Alright, in this video I'm going to talk about the tension versus the force of a nail of a hanging object. And this was a question that somebody wrote in and asked me. They says, what force is more, the tension in a rope or the nail that is holding the object? So for example, if you had an object that was hanging on a wall here like this, what force would be more? Would it be the force on this nail, or would it be the tension in the rope? What would be more? And that's a good question, because the answer to that question is going to depend upon the angle that the ropes make. So the tension in these ropes may be less than the force on that nail, or the tension in these ropes might be more than the force on that nail. It just really depends upon the angle that these are going to make. So we're going to start with a very basic example here. We're going to have an object hanging straight up and down by two ropes, okay? And this is going to be my x, and this is going to be my y-axis. Now I've had a lot of requests here for physics videos lately, and I do other videos. I do, depending upon what I'm teaching a student. I may do chemistry, I may do calculus, I may do linear algebra, statistics, whatever it is, whatever I'm teaching. I'll post videos for my students. So if I'm tutoring with the students in between sessions, I'll post videos. But I get a lot of requests for the physics, and I think it's harder to find physics content out there. I think you can go on YouTube and find 1,000 ways to revolve an object in calculus around the y-axis, or you can go on chemistry and find a lot of ways. But for whatever reason, physics is a little harder to find. I also get a lot of comments from typical comments from students that are, they'll make comments like, or people watching, they'll say, well, I don't want to watch about units and free body diagrams. Just get to the point, or or there's just skip to this part of the video because it's just a rant, and or whatever it is. And that's a typical response by students learning physics. And the reason is that this is a very immature response in the sense that you don't know, when you're dealing with physics, you can't take shortcuts. Okay, there's no, this isn't like chemistry or math. Chemistry or math, you learn how to do the problem once or twice, you can do it, right? It may be difficult, but physics is more difficult because you have to set up the problem correctly. And if you're not using the correct notation, if you're not using the correct axes, if you're not using the correct geometry, if you're not using the correct free body diagram, you don't have a chance to do these problems, okay? So what I'm teaching you here is through years of experience, years of teaching, and that this is a very typical reaction I get from students when they're first learning. They want to learn the shortcut. They don't want to do a free body diagram. They don't want to write the correct forces. They want to try to do everything with a proportion. And those days are over. Proportions were for junior high, and they may have helped serve you, or you can kind of reason your way through things. And when you're dealing with like a chemistry problem, I mean, you can fake your way through that whole problem. I mean, through stoichiometry and volumes of gases, and limiting reagent. I mean, that's really all that it is proportions. To be honest with you, it's direct variation. But physics, you can't do that. Okay. And physics, you need to think of this as a war, okay? And you need to give yourself the proper tools to fight that war, to fight that battle, okay? Because physics, you should think of a physics problem will treat you like a bully. I mean, like I said this before in one of my comments, it'll eat your lunch, punch you in the face, and toss you in the garbage can, and that's what will happen. I've seen all different levels of students through the years. I mean, basic physics, conceptual, all the way through calculus-based. Mechanics, electricity, magnetism. And the one thing in common that I see is the minute students start to disrespect physics in terms of understanding the backstory and the proper form, they just, it literally eats their lunch. And I've seen students come out of physics exams literally in tears because they, underestimated the test or the problem, or whatever it is. So understand that it is important to have good form, just like it's important in sports or anything else to have good form. Okay, there's good form in physics, and that means having the correct notation, the correct units, and this is the right way to do it. So if you don't want to watch the backstory here, or you think this is too long, you can always go to another YouTube channel. There's other physics channels out there. This is free content, and that's just how I'm going to teach it. So if you don't like it, then go to another channel. Okay? All right. So going back to this problem, the tension versus the force of a nail on a hanging object. what we have here is we have this nail here, we have this object hanging, 100 kilograms, okay? And this is the force of gravity acting at this center of mass right here. I have my axis, which shows my y, my positive y, and my positive x, and I typically try to align this axis with the most forces, okay, or in the direction of the net force. Okay, so again, I'm going to talk to you about this. When you have your axes, you want to align them always with, you're either going to align them with the most forces, or you're going to align them with the net force. The net force. In this case, I don't have a net force, okay? So what are we dealing with here? Well, I'm going to be dealing with Newton's first law. Okay, which is the sum of the forces equals 0. And that's also saying an object at rest stays at rest, an object in motion stays in motion, unless a net external force acts upon it. All that that's saying is that the up forces are going to equal the down forces. And I'm going to also use the third law here when I'm dealing with the tension. So this is a good example. So the third law says that the force on, let's just say, an object from 1 to 2 is going to equal the opposite force from 2 to 1. Okay, so this is dealing with the third law. Okay, we see this a lot with gravitation, but on tension we also see it. Now this particular problem, I'm gonna make a few videos on this because I'm gonna show you that the tension will change depending upon the angle that you make. But the first thing we need to do is we need to figure out, well, how do I even find the force on this nail? What force does that even represent? Because I only see one force, right? You only see this one force here? I only see the force of gravity, right? That's it. That's all that we see. But we're trying to find out the force on this object. So what we need to do is we need to define boundaries around our object. So what I've done here is I've created system boundaries around these two objects, okay? So I have one system boundary here and another system boundary here. So I'm going to zoom out here. I'm going to zoom out to, I don't know, like 125. Let's go out to here. So I'm going to call this first system boundary here. I'm going to call this system boundary A. And I'm going to call this system boundary B here. Okay. So this is just going to define two different systems. And I have to do this before I can, you know, find out the force on this little object up into here. Okay. But once that I do that, now I can begin to understand a little bit more what's going on in terms of forces. Okay. So I'm going to use these different colors here to represent this. I'm going to start with green here. So I'm going to show if I cut this object here, now I have two forces that appear, and those are little arrows. Hopefully you can see them. That's the force of tension here, okay? And there's a force of tension here. Okay, there's two of them because I cut the rope. And since I cut it, right, and this is a rope, this is going to prove Newton's third law here. And I'm going to have the tension here and the tension here. These are going to be equal here. Okay. So once I cut that rope, okay, assuming this rope has no mass, that's another caveat here. The rope has no mass. So no mass. Rope has no mass. Rope has no mass. And that's important because it would completely change the problem if it had a mass depending upon where I cut it. But this is a magical rope, so this is a magic rope here, okay? Magic. So we tend to use magic ropes and magic wires and circuits, magic ropes when we're hanging things, because it has no mass. Okay, but a real rope does have mass, okay? So my two tensions, I have my two tensions separated here. I have my, my force of gravity down there. And now what's going on up here? Well, I also have a force up here that's going to appear. I probably drew that arrow a little bit too big, so let's make it a little bit less here. Whatever it is, it should be about twice of that. Okay, so it's going to hang down like this. And let's make that, I don't know, let's make that purple. Okay, and we're going to make these, that's still not good. Let's do this. Let's make this one bigger. Let's make these two bigger. There we go. Okay, so I've got my tensions going up, and my tension's going up here, and my tension's going down here. Now, there's another force acting up here, right? So what force is acting on the top of this nail up here? Well, we have we're going to have a normal force acting up, and that normal force is going to be equal and opposite to this force of gravity. I'm going to prove that to you in a minute. So we're going to have a free body that looks like this, and I'm going to call that now my force normal. I'm going to change the color there. I'm going to make that like a blue. So I'm going to call that my force normal, like this, force normal. Okay. So that's what we're looking for. The question is, how does the normal force here compare to the the tension here in the rope? Because the rope, the tension is going to be the same everywhere. Okay. So that tension's the same as this tension, as this tension. Okay, they're all going to be the same. So when I'm setting up a problem, the first thing that I'm going to do, I'll move these axes over here so I can give myself some room to work here. I'm going to look at boundary or system A here. System A is going to have the normal here with these two tensions. So I've redrawn these arrows so you can see them a little easier here. So on system A, I'm going to draw it over here. I have my system of equations where I'm going to say the sum of the forces in the y equals 0. Okay. So when I'm dealing with this situation, I can do a nice little shortcut here. I can basically say whatever's up is going to equal whatever's down. And that's only because I'm dealing with the first law. There's no net force. So whatever's up, everything that's up is going to equal whatever's down. And the reason I like to do that is that you're able to keep all of the forces positive here. Okay? So for example, I can say the force normal, okay, is going to equal twice the tension. So in this case, the tension, if you want to talk about tension, is going to be half of the normal because they're each taking up half of the slack here, right? So the tension is just going to be half of the normal. That's another way to say that. Okay. So this tension here, since it's being divided by 2, okay, is only going to be half of whatever this is. So that's kind of interesting. So if my tension was 50 and 50, okay, then the normal would be 100. But how does that relate to the weight down here? Let's take a look at that down here. Let's look at B. So if I take a look at my system B down here, I'm going to say the sum of the force y equals 0 again. Okay. So the ups are going to equal the downs. So I'm going to have, in this case, my ups are going to be Ft. So I'll just write it out this time. I'll be like Ft plus Ft is going to equal Fg. So the ups are going to equal the downs. So Ft plus Ft equals Fg. So 2Ft equals Fg. Okay. So now we're starting to get somewhere because we actually have values for my Fg. So my tension, okay, is going to equal Fg over 2. In other words, the tension is going to be exactly half of this weight. So we're going to learn that this is the most efficient way that you can hang an object. If it hangs vertically straight up and down, that's how you're supposed to hang it. Okay, to optimize the tension. We're going to see here that later on the tension is going to change very quickly, and it's going to become very large as we try to change this angle here. Okay, as we try to change the angle from the horizontal here, as we try to change this angle into here, that the tension is going to change. But right now, let's just start with this example. So let's work backwards. These are my problems now written out in notation. So if I go back to this, so I'm going to start working backwards now. So I know mg. What is mg? Well, mg is going to be the weight of this object here, okay? So I have 100, okay, times 9.8. Let's just use 9.8. Okay, so what am I going to have here? Well, this object here is going to weigh 980 newtons. Okay, like this. So if I'm looking at my tension here, I can go ahead and I can plug in that Fg over there. So I can say, okay, my tension is going to be 980 over 2, right? Or it's going to be 490 in this case. So we can start to work backwards here, okay? So my Fg down here, we know that's 980. So my tensions are now going to equal, in this case, my tensions are going to equal 490 each. And you can work right on this free body diagram. That's why I like these free body diagrams are meant for you to work upon when you're doing the problem, right? Now this is where we get into the third law, because you have an equal and opposite reaction here. Okay, this is the third law. Remember we talked about that up here. We said we're going to deal with the first and the third. Well, the first law was dealing with these two parts here. The third law now I'm going to be dealing with this. So now I'm going to be able to keep writing this in, and I can fill in the diagram. Okay, work on your free body, write on it. Okay, physics is already unconventional, so don't feel bad about writing on your free body diagram. That's what it's meant to do. It's meant to give you information. Remember, we're trying to merge the conceptual with the mathematical. Okay, because remember, each problem is unique and it's its own special problem in physics. It's not like math where you learn how to do a couple of problems and they're all basically the same problem. Okay, so going up here on my diagram, I've proven now, okay, that the normal is going to be twice the tension, right? Okay, so the normal here in this case is going to be what? Well, the normal here is going to be 980. Okay, the normal here is going to be 980 because again, I'm doing the first law. Okay, the ups equal the downs. Okay, there's no net force, right? So whatever's up has to equal the two that are down here. Whatever's up here has to equal what's down here. So that might not look too exciting to you, but the important thing is here that I can link my two system boundaries now. That's what's important here. So when we're getting down the road and we're starting to talk about pulleys and different things like that, it's very important to link these two system boundaries together. So you may say, well, what does that mean in this problem? Well, basically I can now relate the normal to this force of gravity down here. You see this down here? So how did they relate? Well, I know that the normal is twice the tension. Okay, so if I take this up here, okay, and I know that twice the tension is also equal to gravity here, I can take this one, okay, this particular equation here, and I can take this one here, and I can combine them. Okay, so I can take system A and system B. I can combine them together, which I'm going to combine over here. So you see twice the tension is gravity, and the normal is twice the tension. So if I combine them, I can say the force of the normal equals twice the tension, and that also equals Fg, right? I'm just combining the two formulas. That's all that I'm doing, right, from up here. So the normal now equals Fg. Okay, and that's important to make that link in our heads here, because we're basically marrying these two worlds together. The world of A and the world of B here are going to come together, and they're going to allow us to come up with this relationship here. And when we're dealing with a system that's moving, dynamics, that's important because we're going to have to determine the net acceleration of the system, and that's going to be linked between the two systems also, in addition to the tension. Okay, in this case, this is a simple example, but this example was just basically asking the question, how does the force on this nail compare to the two tensions here? In this particular example that I showed you, the tension is obviously less than the force normal on this, and the normal is equal to gravity here. So the normal in this case, notice the normal is 980, the gravity is 980. I proved it two ways. I proved it by showing the values on the chart here on the free body, and I also proved it mathematically here. Now what we're going to learn later is that this relationship will hold constant through time. The normal will always equal the force of gravity here. I mean, unless this object is, laying against the wall and friction's helping, that's always going to remain true. So that's always going to be true in this example, right? Always true, even if I change the angles here, even if the tension of the rope starts to change, that relationship never changes. So the force on the nail, or the force normal on the nail, is always going to equal the weight of this hanging object. But the tension now, we're going to learn later, okay, the tension down here, which we calculated as 490, the tension will vary, okay, as that angle changes. As angle changes. Let me scroll down a little bit here. As angle changes. And that is important. And when you're designing objects and you're trying to hang an object from a wall or even a traffic light, I mean, back in the old days, they used to hang traffic lights by 2 cables. The more you can make this angle closer to, when I talk about the angle, I'm talking about this angle here, okay? This angle across it here. The closer you can make that angle to 90 degrees, the safer you're going to make this object, because it's going to be the least tension. As I start to move that angle out, you're going to start to have some problems. There is an angle where the tension can equal this, and then there's the angles where the tension can approach infinity, okay, depending upon how small I want to make this angle. And that's a design question. That's like an engineering question, because when you might not want to hang an object straight up and down just because you don't like the way it looks, okay? But you might want to ask yourself, well, what's the safest way to do that if it's a heavy object? So in the next videos, we're going to start to change this angle theta here, and I'm going to show you how that tension will change over time. And then I'm going to go ahead and I'm going to graph this for you. I'm going to do a whole lab here with you on this. I'm going to take Microsoft Excel, and I'm actually going to show you the function of tension versus this angle theta over time, and then you'll be able to see for yourself how that tension varies over time and how the normal will not change. It will always be equal to gravity. All right, that's all I've got for this video. Thanks for watching, and I'll talk to you soon.